So today we're going to talk about an interesting intersection between Poisson regression and survival analysis. There's some aspects to this that are cool, some aspects that are kind of like, why would we do this? And so I'll explain why would we do this at the appropriate intersections, points where that makes sense. So, we started here kind of at the end of the last lecture, just kind of reviewing some of the basic components of survival analysis and what that was about, kind of detached from the Cox model, right? The survival function is this decreasing thing that goes from 1 to 0 or 100% to 0%, or however you want to think about it, where everyone starts off surviving, which is alive, disease-free, whatever, and this is declining function over time, right? And then we also had talked about, or Dr. K had talked about the hazard function, right? Which is this rate. It's the rate of failures, right? So it's really it's effectively the slope of the survival function at any given point in time, and it's the instantaneous rate of failure here, as it says. And we also had covered that there's this relationship between the survival function and the hazard function, and basically that survival function is e to the minus of the integral, the sum effectively of these continuous, the instantaneous hazards. Okay, so this is how you get from a hazard function to a survival function. And so these are just relationships put out earlier, and this picture is interesting because I would surmise that this picture effectively, this is a picture of AIDS survival in an era before therapy, and the shape of this picture is what I would call exponential survival, where basically you have this very steep kind of curving piece here. Notice there's no nuances, where there's no shape of interest other than it's just descent, right? This is looking like an exponential decay function, which, if you remember chemistry or the other sciences, right, this kind of shape comes up in other places. And this is the type of survival, exponential survival, that we're going to talk about today when we relate to Poisson regression. And so I just want to go over some other relationships that I'm sure you've seen before in your time here, but just to bring them all into one place so it can make sense for Poisson regression and survival here. There's this formula that lets us relate the rate of disease occurrence to the risk of occurrence, right? Rate and risk are very special terms in epi, and even though if they're not always in common language, right? And the idea is that the rate describes the occurrence per some time unit, and the risk is really often talked about in a fixed time period, right? The 5-year risk, the 10-year risk, the risk next week, rather than the disease occurs at this rate, this much disease per person years or whatnot. And there's this formula, that lets us rather precisely relate the risk in a given fixed interval to the rate. And it's 1 minus e to the minus lambda t, right? And this formula, which should also seem familiar from financial formulas that you've seen before, really relates a rate to the risk in a fixed time period. So, and we've seen that when the disease is rare, you can kind of cheat on this formula by saying the rate times time approximately equals the risk. Okay, so just for example here, imagine you say that this is fictional, but let's say the rate of the common cold in a given year was about 23.6 cases per 100 people, so say a quarter of people get sick a year. Let's say this was a rate of getting the cold. Then from this formula, you can look at the 1-year risk of getting a cold, the 5-year risk, the 10-year risk, and so forth, by using this kind of relationship, this formula, 1 minus e to the minus rate times time. So this handy formula, which you should store in your head or on the back of an envelope, lets you make a lot of on-the-fly calculations that let you move between risk and rate in general in your epi life. And I'll get to that in a moment. I just want to say again that this formula, the rate times time formula, doesn't really hold so well for it's not going to really work here for a common occurring thing like the common cold, because the rate times time here exceeds 1, right? So 5 times 0.236 exceeds 1. You can't really have a risk greater than 1. It doesn't really make sense. So it just doesn't work for a common thing. But if the disease was rare, if it happened 1 to 1 in 10,000 people per year, then in 5 years it's basically 5 in 10,000, more or less. You could get away with it. But for the common stuff, this is the appropriate formula. This is the appropriate formula here: 1 minus e to the minus lambda t. And there's an assumption to this, which is that the rate doesn't change over time, right? Like my 1-year risk is this rate. Using this formula, it's this rate brought it forward 1 year, or the 5-year risk is the same rate brought forward 5 years, and so forth. We have this assumption, effectively, when we use these kind of formulas, that the rate is just this time invariant thing. The more years of exposure you have more years subject to that rate, and your risk is this goes by this formula. And that's interesting. So when we think about Poisson regression, we're modeling a rate, and in Poisson regression, have we really dealt with the rate changing as a function of time? And we haven't really. We happen to be a person time is this thing to look at and control for, but we never are modeling a time-dependent rate. It's always just the rate is equal to this e to the minus linear formula. We haven't really dealt with that. In the Cox proportional hazards model, does the rate change over time? It does. So if you remember, there's this thing called the baseline hazard function. That's the h sub 0 parentheses t. Well, that parentheses t business is letting it's defining the hazard function over time for the group that has a 0 for every other covariate. It's like an intercept, actually. I'm not sure if it was presented that way, but it's like the intercept. It's this base rate of disease in your study when you're doing the Cox model. This h naught of t function is a time-dependent function, and it lets the rate change over time. So the Cox model allows the rate to change over time. That's really important because I think in one of the examples that was shown, there's a surgical intervention, and the rate of death after surgery might be very, very different in those first few days than after that period. Let's say the 1-day hazard might be very different than the 2 to 20-day hazard. And so the ability to have the survival rate and the hazard change over time could be really important sometimes when we're looking at survival analysis. The Cox model rates that we've looked at so far, the Poisson model rates, don't really deal with the rate changing over time. And when we do this kind of reasoning, we also assume the rate doesn't change over time. Right, we're just saying that the risk changes over time, right? The more years, if it's a 5-year risk versus a 10-year risk, yeah, the risk goes up. But the rate, the disease-producing process, this 0.236, is the same over time. So the risk is changing over time because it's 5 years, 10 years, but the rate is the same. And we have a way to model that, which is we have a modeling structure that deals with a constant rate, and it's actually Poisson regression. So, if we can get risk over time, we have 1 minus e to the minus lambda t. We can very, very easily get survival in a given time by this really easy formula called survival is 1 minus risk, right? So it's the opposite of getting the disease is not getting the disease, and so the 5-year survival from getting a common cold is 1 minus the 5-year risk of getting a common cold, right? It's just the opposite. That's what's on the bottom here. Again, this isn't too earth-shattering, and if you substitute 1 minus e to the minus lambda t here, you get 1 minus, these ones cancel out, and then you actually wind up getting e to the minus lambda t here. And so you see what you get is this relationship that survival over time is e to the minus lambda t under this idea of constant survival, if the constant rate, that is. The survival function is is just e to the minus lambda t, which, by the way, this looks kind of sort of like it looks sort of like this other relationship here. Okay, notice these are very, very similar. Okay, this is the relationship we showed for Cox regression, and here is when you assume a constant rate of disease. You have that survival is e to the minus lambda t. So here that we have the 1 year risk of getting the cold was 0.21. The 1 year survival risk, the chance of not getting the cold, is 0.79, and this is a declining function as you consider a broader time span. So it's going to go down to 9%. Making it out 10 years without getting a cold is a 9%. You have a 9% chance of surviving, that far ahead. So this is just algebraic observations from earlier concepts of how risk and rate relate. We can also easily just talk about survival. Often in other epi courses, it's not shown as S of t. It's usually just thought of the risk in some time period. But here, if you take 1 minus that, you get the survival function. So, so thinking about what we've done so far, when we think about the proportional hazards model, which is over here, it's a model of the hazard function, right? It's the hazard function at some time given the n some x's is equal to the baseline hazard at that time times this e to the minus our usual e to the exponent here of our betas times x's. This is our Cox proportional hazards model. This is a model for the failure rate. Okay, sorry. And we estimate our betas by maximum likelihood regression. And then we, as I just said before, we have this thing called the baseline hazard function that is h naught of t, and it's not directly specified. It's just kind of estimated using a Kaplan-Meier-like approach. And it describes the hazard over time for the baseline group, the group where all the x's are zeros. That's really what the baseline hazard function is. If you made a Kaplan-Meier curve for the people that have x equals 0 for every x, if you made a Kaplan-Meier curve for those people, you would get the baseline hazard function. So this is one model that we've talked about to model the hazard. And the hazard basically is the failure rate. It's the conditional failure rate, but it's effectively, you can talk about it as the function. The hazard function describes the failure rate over time. But you can imagine a modification to this function which looked something sort of like this. Imagine the baseline hazard was 1 or some constant. Let's just imagine it was 1. Then you'd basically be left with something like this. H of t is equal to e to the same linear function. So I'm just replacing this with a 1. Okay. If you substituted this time-dependent function with a constant, 1, 6, whatever you want to call it, what you're going to get is a model that looks a whole lot like another model that we know, which is basically the Poisson model. Right? This is this e to this nice linear function modeling a rate. Rate equals e to this function is basically the Poisson regression model. So to get from a Cox model to something that starts to feel a whole lot like a Poisson model, you have to say, well, the rate is no longer this time-dependent baseline hazard thing, it's a constant. And if let's say it was not 1, but let's say this was equal to 0.5, you could have a 0.5 times this, and you can actually put the 0.5 into the exponent as an intercept term. Right? It'd be e to the, e to the point, or e to the log of 0.5. If you had a non-1 constant, it can go in the exponent here, and it would be the intercept. So basically, all I'm trying to say is if you relax the assumption that the hazard, the baseline hazard, is this time-dependent thing, then you wind up with the Poisson model. Okay? So we'll talk about what this assumption means and looks like. But basically, if your disease process is not the rate is not time-dependent. Let's say you're modeling the cold, and the cold, let's say the cold didn't have seasonality, which it does, or if at least year to year the risk was the same, or let's say it's traffic accidents and during a period where things are relatively consistent from year to year, if the rate is not itself a time-evolving process, then you could conduct survival analysis using a Poisson model. So that's going to be where we're going here. It's not always the case that this thing called this baseline hazard rate is itself a function of time. It could be constant. And what we're going to do is we're going to reformulate survival data and try and fit it using Poisson regression. Okay, and what that would have to look like is let's say again, this is an interesting exercise because we're starting with individual data, which we could use a Cox model for. I'm just going to show you how do you do Poisson regression, but there's other uses for this. But if let's say you had individual level survival data, you can categorize the predictor variables and make groups at combinations of predictors, right? So if you had a survival data set with individual observations, but people are male, female, different age buckets, you can summarize all of the covariate patterns in the individual level data set, and then you could sum the number of events and the amount of person time in those subgroups, and you can make kind of this like subgroup data set similar to what we've done, what we've seen for Poisson regression. So you sum up all the 0-1 failures that people had, right? Some people are censored, so they're 0, and the failures are 1s. You sum up all the 0-1s. You sum up every person's time into person time, and then you could actually fit a Poisson regression to the summarized survival data using categorical predictors, or you can treat some of them as ordinal, as we've seen. So you can take an individual data set and actually summarize it using any of your favorite SAS summary procedures or Excel or whatever, and make a summary data set for Poisson regression. Okay, so that's that's what we're going to walk through here. And so again, we have, here's one way to represent the Poisson regression model. The log of the rate is equal to the intercept plus the sums of these betas times x's. This, again, as we just motivated, is you can just think of this as an exponential parametric proportional hazard survival model, where the h0 of t term goes away, and now it's just the survival rate, the hazard rate is equal to e to the beta naught, or intercept, plus the sums of the beta x's. Okay, so this, or we can take this down to survival mode, which we'll do in a second. So this is just, once you have your data summarized that way, you can fit a Poisson model and you'll be doing a survival analysis. The h0 of t goes away because it is a constant. It becomes the intercept up in here, right? The e to the beta naught. Remember, the Cox model has no constant intercept here. It's way back a few slides, but the Cox model has no intercept. It has h0 of t, this time-dependent intercept thing, okay, which is called the baseline hazard. Now that we're going to say that, well, actually the hazard's a constant, the baseline hazard's a constant, we're going to just put it up in here as in the exponent piece. You didn't have to do it. You could have called it log of beta naught times e to this other stuff, but we're not going to do that. And here it is, e to the beta naught plus all this stuff. So this is the same Poisson model, but we're just going to think of it as a survival model for now. And when you have, we've already said that this is the relationship S of t equals e to the minus lambda t when you have a constant hazard. So whatever we get out of our Poisson regression, which is solving for these coefficients that let us estimate lambda, you can plug in here. And what you can get is this nice little equation, e to the minus t times e to the, so this, you're going up 2 levels of the staircase here, 2 exponents up, to the linear function. This is the survival function for a Poisson regression survival analysis. So you have survival data, you can fit Poisson regression to it, and if you want survival curves, this is how you do it. Okay, it's e to the minus lambda t, same basic formula, and you plug in for lambda the Poisson equation, which is effectively, well, we're solving for log of lambda, but you exponent exponentiate here, and you can plug this in, and bam, here you go, survival curves. So we'll make some survival curves today. So this is a way, if your Poisson regression doesn't have to be survival data, right? It could be horse kicks, it could be all sorts of not necessarily survival type. You could just be modeling counts of stuff, the chromosome breaks, other things that aren't survival oriented. But if you are truly looking at survival type data, you can summarize it and fit a Poisson model under the constant hazards assumption, which, if it's true, which we'll talk about, is it true? But if it were true, you can do all this, you can spare the Cox model and just go right to the Poisson model here. And sometimes you have to do this, which we'll talk about. So here, so the Poisson survival approach has some advantages. You can fit a survival analysis to grouped data. Okay, so what if someone only gave you summarized survival data? You don't have individual prospective cohort stuff, which is expensive possibly to collect. What if you had to hear it? What if you just were given a summary table of STI rates in a cohort or in a clinical sample? Sometimes I deal with STI clinic data, and you might just get summarized data from a clinic that's not individual response, following individuals over time with very nuanced data in the way that we're used to for Cox modeling. What if you're just given summary tables of, yes, this much clinic visits, this many tests, this many cases? You can answer survival type questions. You can look at time to development of this condition in aggregated prospective data. And that's kind of cool. So you can make a survival curve, right? Using these relationships, we can fit a Poisson model and make a survival curve out of this aggregate summary data if it's appropriate for a survival analysis. So it's got to be prospective, it's got to be looking at the counts of failures and so forth. This method still addresses censoring, right? So because when we think about how rates work, when we calculate rates and rate ratios, even back to EPI1, if somebody's censored before, let's say it's a 2-year study and someone's censored at 1 year, well, they only count to the denominator at 1 year, right? The rate is penalized in some way because they count less towards a denominator, right? So the beauty of rates always has been that it accounts for censoring. It doesn't look at all of this. It doesn't look at censoring in the nuanced way that the Kaplan-Meier method and the Cox method does, where we look at censoring in every interval. But this method still actually is adjusting for the censoring issues that we're worried about with survival analysis, because when people drop out of a study, the person time is not seen either. And so there's this assumption perhaps under the hood that the censoring process is uniform over time, or you can make this, there's some nuances to what that means, but we are adjusting for censoring. So that's pretty cool. And actually we'll give the same answers as the Cox model when the predictors are treated categorically. And maybe as we saw before, when sometimes you can do pretty cool things with ordinal covariates, but generally Poisson regression for this type of data analysis is typically on categorical predictors, and the hazard is constant. If the constant rate, if the H naught of t does not actually vary with t, there is just a constant hazard rate, then you will get the same answer between the Poisson and the Cox survival models. Same answer. So the disadvantages are that you may not want to categorize your variables, and the idea of time-dependent variables doesn't really exist so well. It doesn't. This idea of the extended Cox and some of the cool time interactions that we were dealing with aren't really possible in the Poisson survival model. So one thing is the idea of time interaction inherently is kind of impossible, because that means the rate changes over time. The whole point of the time interactions is to allow the rate ratio and the rates to change over time. That's when we do in the extended Cox model times t or times t squared or whatever, we're inherently breaking the constant hazard assumption. That doesn't work. The one type of time dependency that you can deal with in the Poisson model is that, imagine if you had people changing those internal covariates where your treatment status can change over time. So remember the heart transplant example where you start off not having a transplant and then suddenly you have a transplant and now we switch the tracks on what your exposure is. You could still potentially do that in the Poisson model by moving the person time to different subgroups. So what that means is, let's say I spent 2 person years as a no transplant person and 4 person years as a transplant person. In making your summary data, you could imagine a situation where you say, okay, you gave 2 years to that group and you gave 4 years to that group. So the internal time-dependent variables, you can do it, but you got to do some work. But you can't do the time-dependent interactions for sure. And the biggest disadvantage is that this assumption may not make any sense. The constant hazards assumption. You need to have a you need to be fairly confident that the hazard itself is not changing over time. And so for very micro types of processes, like again, a surgical intervention where the hazard, the force of of bad stuff happening really could change in the short term, right? You have a surgery and you're on the table and you're anesthesia and you're like this, and you're very vulnerable for a few days. But once you're on the floor, you're doing better, and maybe the rate's quite different a week later. That situation where there's this very micro process happening and the rate is this fluctuating process is not good for Poisson survival. It may be good at this very zoomed out level. You have tables of cancer survival in a state, and you're trying to make survival curves X years out for people in this jurisdiction that have cancer, and you have some aggregate survival process data. At that very hot air balloon level, we are looking at a population's survival experience. I think the constant hazards assumption works out better. But if you're really tracking very minute, it's a clinical trial and you're trying to model a very short-term survival process, Poisson's not for you because of this constant hazards assumption. Too strict, not good. So I'm going to work through an example of this. Which over here, and this is actually the original data that was up to motivate survival back on day 1 of survival analysis. I did not make this slide, as you might imagine. This is an old slide, and it's about leukemia patients. Okay, so 2 groups of leukemia patients. It's a study. Half of them get placebo, half of them get treatment. This would never happen in 2015. You would never not treat someone, with leukemia. But this is a time. So leukemia therapies were quite different prior to 1990, so this is that era, is denoted by the Xerox specs. And so here was the 2 groups, 21 in each group. Notice the placebo folks are not doing too well here. The plus sign meant censored. And so when there's no plus sign, that means dead. So here is the survival times, or not dead, fall out of remission, not dead, sorry. But not doing so well. They're in cancer mode again. And notice these aren't very long times either. Whereas the survival times are longer for those on therapy, and many of the ones on the high end are censored because the study ran out of time and they're still doing well. So that's the data over here. And so this was the original survival example. And so when this was originally done, it was all in the mode of Kaplan-Meier, Cox modeling. But another way you could have approached the data was actually just by computing rates and rate ratios, right? This is before you were thinking about the very individual per person experiences. A very reasonable thing that you might have done walking into this course is do something like this. We said, okay, cool, I got some data here. I got 9 failures and I got 359 person weeks. And so that looks to me like a rate of 0.0251. And whoa, these people have 21 failures and 182 person weeks. That to me looks like a rate of 0.1154. And you might have done something like this. Let's look at the rate ratio comparing the placebo to the treatment. Wow, 4.6-fold higher rate. It looks like we should really give people therapy. So this is like maybe an Epi 534 approach to the same information that wasn't really explicitly talked about at this time because we were talking about Kaplan-Meier stuff. But this is potentially a reasonable thing to do and not necessarily wrong per se, except when we do this kind of thing, which is, again, it's what we might have done last semester, this is really wearing your Poisson regression hat in some sense. We're looking at a kind of constant rate. We're talking about rates and person time. Every time we were doing this, in Poisson regression or in previous courses, there was this idea, there was this big assumption when we did this, which is the constant hazards assumption, that this rate of 0.1154 uniformly describes everyone in this group at every time, right? No matter how many weeks into your course you are, you face the same rate. If you're 12 weeks in, if you're 2 weeks in, or whatever, the rate for this group happens to be 0.1154, right? And the rate on the left side is 0.0251. No matter where you are in time, this is your rate for you. Everyone in this column has the same rate, and we estimate it by doing the sum of failures over the sum of time. So this was an assumption that no one ever talked about in any of the courses, and you've been lied to, which is that the rate is always been assumed to be just independent of time. No matter where, and again, for something like a trial where you're doing this like point intervention and then like watching a process develop, this may not be the best idea. But it is. This is definitely part of our toolkit, these rates and rate ratios. So this is the data set from earlier. And so we have some choices here. If we want to model this, we could do a Cox proportional hazards model. It would look something like this. The H of t is H naught of t times e to the beta 1 times x1. There's only one covariate. It's either on treatment or you're not. Here in this coding that we'll show you, we're going to do placebo is 1, just so you can get the ratio above 1. Even though placebo is bad, we're going to be pessimists today and show that placebo puts you at 4.6-fold the risk of falling out of remission. So 1 is placebo, 0 is treatment. You can alternatively model these same data using Poisson regression, using the grouped experience data of the two treatment groups. Okay, and that's what I'll show you as well. And that would be the log of the rate is beta naught plus beta 1 x1. Okay, so what you do is, this is now your data, these rates basically. It's the summarized experiences, 9 and 359. This is going to become your offset, log of 359, and 9 is the count in the group. Okay, so the count of the failures, though it says failures, and that is incorrect. It should say failures, and the count of that is 9. And this becomes the new data, the grouped experiences of the people. Okay, so this is the idea here. And if these were both equally reasonable approaches, if you had this exponential baseline hazard, or it's really if the baseline hazard is constant, is really what it should say. If you have this exponential survival constant baseline hazard, I'm just going to say that, then we expect for both models to get the same answer, right? Which is that the hazard ratio equals the rate ratio, which would look something like the rate of placebo over the rate of treatment, and this would all be equal to e to the beta 1. All the e to the beta 1s would be the same, and it should be about 4.6. If it is true that the constant hazard assumption is right, that the hazard, that there is just this constant force of infection or illness or whatever you want to call it, force of bad stuff happening. So here is the data in pH reg. So this is the analysis that you would do if you fit pH reg to the survival data. Here we have proc pH reg data equals Anderson. Okay, the reference group again is going to be the treated. It says placebo versus treatment, and survival time by status treatment. Okay, this is a basic pH reg Cox model, one X variable treatment. Okay, here you go. Hazard ratio of 4.5. Okay, that's what you would get when you fit the Cox model to this. So 4.5-fold higher risk. And when you assess the Cox proportional hazards assumption, which I think this must have been, there was a variant of this at some point in the past, because this is all old news. What you see is parallel log-log curves. That looks great. It's beautiful. And you'd say, great, the Cox proportional hazards assumption is met. Now, this is not the constant hazards assumption. This is the proportional hazards assumption. Okay, so I guess I have to underscore that. There are two different assumptions. There's the proportional hazards and then the constant hazards. And we'll spend a moment on that in a moment, because I want to like nail down those differences because they're important. This is the old assumption that we used to talk about for the Cox model, which is that the hazard ratio is constant over time. The hazard ratio is constant, not the hazard. And that the constant ratio of the hazards, this is called the proportional hazards assumption, and that was explicitly about the Cox model. And that was assessed amongst other ways with the log-log survival curves, because this kind of linearized things, basically. This undoes that double exponential that we saw way back like 6 slides ago, that e to the e to the. Well, we're going to undo the e to the with a log-log, and that should straighten things out, and you should get these straight, nice parallel, just parallel. This straightness doesn't matter as much, but it's just really these parallel kind of curves here. So this is what the old way of doing it. Cox proportional hazards meets model, and it meets the assumption. Looks great, 4.5. So here's a way to do the same analysis using Poisson regression. And what you first got to do is you'd have to summarize the data here. So you'd say, here's one way to do it, proc means. You're going to summarize by treatment status. So class Rx is going to be, hey, proc means I want you to collapse along treatment. And then summarize status. This is the number. This is the censored 0, 1 is failure. So you want that. This is going to summarize all of the status variables in a group, and you're going to summarize all the survival times. Okay, and then that's actually this for the SAS folks here. That people like SAS and get excited about SAS, which I'm not sure how many of you are. These are two different. You have to ask for it twice. If you want to make an output data set, which is what I want to make. On this line, on the proc means line, when you say sum, mean, whatever, this controls what gets put on the screen, which is nice to look at on the screen. But if you want to make a data set out of the summarized experiences of people, you got to use the output line, and then you do sum of status and survival time equals some. You can make up new variable names here. These become the analytic pieces in your Poisson survival analysis. Okay, so here we're using proc means, we're summarizing by treatment group. There's only 2 treatment groups, and that's the only covariate pattern that exists, is just which treatments you're in. So there's only 2 lines of data. It's kind of boring. This is the data set that you get, right? It's just the experience of the treated and the experience of the placebo. And when you use proc means like this, by the way, when you make an output statement, and when you have output with a class statement, it does this business with types. Have people encountered this before? These things, underscore type. It's these automatic variables. Basically, it keeps track of the stratification that proc means is doing in the class statement. So if you say class, treatment, sex, blah, you have 6 things, then it's going to do all of the pairwise stratifications, and it makes a big mess. You have to use these, you have to filter some of this out. If you just want the fully stratified data, you need to use the where statement and subset what proc means creates. So here, you have to say where type equals 1. Just try this out at home. You'll see what I mean. I have to like show you in SAS and show SAS doing annoying things. Then this is going to be me showing you how to undo what SAS does that's annoying. You have to use the second data set. This cleans up, this restricts to just the stratified by treatment type rows, and then you compute the log of survival time, because that's going to be the offset in our Poisson model. Okay, so what we've done here is I'm just instructing SAS to summarize all the cases, summarize all the person times, And here we go, and it's going to basically say here, survival time in weeks. Here's the summary pieces, and then here these are the denominators. Here is the numerators, the number of people that relapse, 9, 21, and so forth. And then because we're doing Poisson analysis, survival analysis, we're going to have to use an offset that's the log of this column, natural log 359, 5.888, and so forth. Okay, so we need these three pieces to really do our analysis. And so we're going to use proc means and then data set to clean it up. So again, something to keep in mind is, if you have the data as individual data, why would you bother doing this? Honestly, it's not that the Cox model is a little more robust than Poisson because it doesn't have the constant hazards assumption, which is more restrictive than the proportional hazards. So the real beauty of the Poisson model is, what if the data only came to you this way? And there's situations, a lot of them are really about surveillance and when you get summarized data, that the data comes to you as a summary survival data set, and you don't have Cox proportional hazards as your choice. So I'm showing you how to make a summary data set out of higher quality individual data. Right? It's kind of higher quality. You'd prefer to have every single person in the state's cancer data, but at the line by line level, including all sorts of people that don't have cancer and all that. But instead, you have a survival summary table. You'd prefer to have the individual data, but sometimes you just get this. Number of failures, amount of time at risk. And so this is perhaps a silly exercise to the extent that we took good individual level quality data and then we made summary data, but it's really to show the principles, and really often in life someone just plunks this on your desk and now you got to do a survival analysis. So this is what you would do if you wanted to make summarized data for Poisson survival analysis. Okay, so what you do is, this is the same, this is our Cox model, but now it's just redone as a Poisson model. We have class treatment, placebo is 1, 0 is treatment. So it's going to be, again, this greater than 1 effect, because it's placebo is not good for you. And here we have model status sum. This was the sum of all of the failures, the count of the failures, equals treatment. Offset equals log of person time, survival time. Link equals log dist Poisson. Okay, so this is standard Poisson regression stuff. And lo and behold, we get 4.6. Okay, so 4.6, if you remember, was the unadjusted rate ratio that we computed manually. This, 4.6. So there it is again, 4.6. It's a little unglorious because there's no other control variables. We're actually controlling for anything, so you get kind of what you could have done by hand. Right? We got the unadjusted rate ratio for effectively a 2x2 kind of rates table thing. This isn't that interesting because there's no other covariates. But this is exactly what you would get from doing the manual kind of unadjusted approach that we did over there with 4.6. Also notice this is really similar to the 4.5 from the Cox model. So actually, the constant hazards assumption perhaps applies here. And we'll explore that in a few more slides. So 4.5 versus 4.6 is actually kind of similar. So what's cool here is, whereas logistic regression and survival analysis were both analyzing individual 0-1 experiences. Remember, Poisson regression is modeling the group experience, the sum of all the zeros and the ones. And so now we've modeled the sum of all the failures, the sum of all those individual people's yeses and nos. The sum of their failure experience is now being modeled as a unit, as a row. And so we're looking at the entire number of failures in the treatment group, offset by the log of the person time in the treatment group. And again, you could expand this to other covariates if you had stratifications by sex, age, whatever. Those could become additional covariates, and you can do a survival analysis this way. And in this case, you kind of get the same answer, which is kind of cool. Maybe it's cool. It's nice when things kind of tell the same story, and this is a robust, now you have two answers that get you to similar places, and you should feel good about that. Here we go. What's cool about this is, we have some interesting pieces of information here. We have the estimates of the intercept. We have estimates of beta 1, which is the slope, the parameter for treatment. And we can use these to graph the survival function as well, right? We'll talk about that. I think it's coming up there. It's coming up. There it is. It's exciting. So we get some cool pieces of output from Poisson regression. We get what it calls the rate ratio, but it's really the hazard ratio. Okay, so that's one cool thing. We get the hazard ratio, even though it's Poisson, we're going to call it. Doesn't matter really anymore. The hazard rate is a rate. It's called the rate ratio. We're getting a rate ratio, and it's all the same stuff. Okay, so that's pretty cool. And then these estimates, the estimates for the model coefficients themselves are useful for making an adjusted survival curve. Okay, you can just grab these and directly plot the function. That's the e to the linear function. That's going to give you the survival curve estimated from Poisson regression, and we'll do that. We'll graph that too. Okay, so this is really cool. If the data, if the data only comes to you as grouped and it's survival type data and it's grouped, this is really cool. It's also cool if the constant hazards assumption is appropriate, right? It looks like in this situation, 4.5 and 4.6 would suggest that probably the assumption's okay. It doesn't prove it, but it suggests you're getting a consistent answer by two methods. You'd say, it's probably okay. But we actually have more formal ways to assess that in these data, which is, if you have exponential survival, then we have S of t equals e to the minus lambda t. Okay, so exponential survival is the same as constant hazards. I may have said both, right, at different points because of this relationship. If you have a constant hazard, you have exponential survival. Okay, that's the same assumption. So if we have a constant hazard, it looks like this. The log of S of t is equal to minus lambda t. The log of survival is basically linear, this linear function with time, negative lambda times t. If this is true, that you have a single lambda, this single constant rate thing. If you have a constant rate, you have exponential survival. The log of the survival is linear. Okay, so you can assess this exponential assumption or the constant hazards assumption, whatever you want to call it, by plotting the Kaplan-Meier curves and taking the log of the survival values, otherwise known as the log survival curves. Not the log-log survival curves, but the log survival curves. So if you looked into proc life test and you do the plots option, there's the log-log survival, which is what we've been using for assessing proportional hazards. You could also tell it to give you just log survival. And log survival is useful for assessing this other assumption, the assumption underlying the Poisson model of constant hazard or exponential survival. If this thing is linear, then we would say we have constant hazard and the Poisson model should apply. So here we go. This is the log survival, or negative log survival, not the log-log, for the remission data. And these are linear. So not looking for parallel anymore, we're looking for linear. And these are linear, which would suggest that the hazard rates in each group are constant. That there's one constant hazard thing that's this, and there's another constant hazard thing that's this, and the whole point is we're getting the rate ratio, which is the ratio of their two rates, but each group has its own time invariant constant rate. And that is supposed to be linear if this relationship holds true, right? The log of S of t would be minus lambda times t. Okay, so the slope of this thing basically is lambda. Okay, so the slope of this actually would also be the rate. If this is linear, this time scale is time, this thing is minus lambda t. Sorry, I'm going the wrong direction. Okay, so this needs to be linear. If this is curved or otherwise funky, then it is a violation of the constant hazards assumption / the exponential survival assumption. Why does this go through 0? There's no intercept. This is a linear, this is a line with no intercept, with no y-intercept. It's just got a slope, and the slope is lambda. So anyway, but the point is you're looking for linear, not really parallel. You're looking for linear now on the log survival curves. And if you assess this and it's linear, you say, okay, I think this looks like it might be a candidate for constant hazard or Poisson, otherwise known as a Poisson regression type model. Now, one luxury of this is that you actually can only really assess this on the data if you have individual response data. So I said, actually, one of the reasons you'd use Poisson regression is you only have available to you summary data. You don't have individual kind of time course data through a study. You can only make this picture when you have that individual data. So it's a little bit of a catch-22. So if you're given the data one way, you're stuck in Poisson mode, and you're not really able to assess it with these individual plots. But that's the trade-off. When you have summary data, it's a reduction of information. You have just aggregated experiences, and all you can do is assume a constant rate in the groups. You can't actually, you don't have individual follow-up time. That would have cost you 50 times the budget, and you don't have it, and now you're stuck assuming constant hazards. Okay, that's actually a real trade-off in study design. You couldn't do a cohort, way too expensive, way fewer people. Instead, we might have a summary thing. You might have a surveillance system that's detecting sentinel things from some health system. You're stuck in a constant rate, survival kind of analysis mode. You don't do individual follow-up time. So that's a real trade-off, and I don't know what to tell you, other than what happens is once you assume Poisson for that aggregate data, you can't assess the assumption so well with these plots. You can't at all, actually. So here we have the luxury of having the individual data and saying, oh, which model should we choose? Should we choose Cox? Should we choose Poisson? Here, the answer is Poisson is valid because this is linear, and you get the same answer, 4.5, 4.6. It's all good. So this is really a luxury that you have only in certain situations. So the other thing that we talked about is another way to actually look at the survival assumption, the constant rate or the exponential survival assumption is you can actually just plot the survival curves and compare it. You can compare what you get from the Poisson model, the curves, and compare it to Kaplan-Meier survival curves. And what I mean by that is this. We said earlier this is, survival is e to the minus lambda t, and you can plug in for lambda, you can plug in what you get from the Poisson model, because this is the model of lambda. And so if you do that, you can plug in, minus 3.69 for the beta naught, and you plug in 1.53 for beta 1. And you could graph that. And that's actually what I'm doing here. So this is a little data step that's making observations at different time points from time 0 to 35 by 0.1 increments. And it's making treatment group 0, and this is the curve for treatment group 0. They have an intercept, 3.861. And here, and then it's making output means make a row, and then it's making the treatment group Rx equals 1, and then this is the survival observations at every time point for Rx equals 1 for treatment group 1. And this again here's beta 1, the estimate of beta 1. So this is making basically 350. So observations for each group. So it's making 35 time points at 1.1 increments. So 350 observations of treatment, 350 observations of treatment 0 and treatment 1. And so we're going to have values of t, and then we're going to have values of s at each piece of t. I'm just graphing this, making a data set with lots of points to graph using the information from the survival curve. And why am I doing this? Because we get to do something cool like this. Okay, the curvy line is what the exponential, this function looks like. Okay, so the red one is treatment group 1. So this is the placebo folks. They're not doing so hot. Okay, here's the placebo group. And, there it is. Okay, this is the data step that made this, that was the observations in the data step that we're making that have the beta 1 term in here result in this picture. This exponential thing is the Poisson regression predicted survival function. And here is the other one for the treated group. They're doing better. Okay, so here at time point 30, you see, you still have, if you extrapolate out to here at time point 30, you have about half of the cohort surviving still. Here is the Kaplan-Meier data on this. There's the same data set with Kaplan-Meier estimates. This is what was shown way back, at the beginning of survival. Notice the exponential, the Poisson survival hits right through the Kaplan-Meier. Okay, so this is like another graphical approach. If you're able to reproduce from the Poisson analysis something that goes smack through what you'd get out of a Kaplan-Meier, or if you were doing more adjustment, you'd have an adjusted survival step function from a Cox model using the baseline statement and pH reg and all that stuff that we've talked about in lab around adjusted survival curves. You could basically come up with a curve out of Cox regression, and you can come up with one out of Poisson, and if they agree in some way, then you say, hey, that looks pretty good. And again, I think this looks pretty good. Like this really kind of, the blue curvy exponential survival hits right through the Kaplan-Meier estimates. So notice this is the data. I mean, this literally, this step thing is it's the Kaplan-Meier estimator. It is a reflection of the data. You made a table that's this summary row by row, what's going on over time. This is almost like a scatter plot in a sense of the data. If you can make a scatter plot for survival, right, that's the Kaplan-Meier process. It's trying to make a simple graphical summary of the experience. And here we have one number, literally, that is able to hit right through all of that. So that's pretty cool, right? When you think about it, this is a model, this is an assumption. It's got way less information. All it's got is this one number, really, minus 3.7, and it's able to describe the nuances of the data really well. So that's actually really cool when you think about it. That's one of maybe perhaps the power of the Poisson model is it has, it doesn't have this H naught of T thing. This H naught of T thing bakes in this step function for some referent group, and it's very data dependent. It's dependent on your data set. The Kaplan-Meier step function is a scatter plot of your data, and that's basically what the H naught T is in the baseline hazard. And when you do Cox regression, you're building in this scatter plot of the data. The Poisson model doesn't have that. It's got alpha, and it's got beta, and it's got all that other stuff, and it doesn't build in all of this detail of the Kaplan-Meier estimator. So there's a simplicity aspect to this that's kind of cool. That with one magic number, we describe the data, and then here with two magic numbers, we describe the placebo group. So there's a simplicity, coolness to this. You get one nice smooth function. Yeah, you miss some of the nooks and crannies of this step function, but by and large, it's kind of good. So there's something that maybe feels good about that. That you've described the data simpler and efficiently, but maybe oh no, I missed this. I missed something over here because the curve is under or something. You might worry about a few pieces, but this looks on the whole pretty good. So here, if case you're interested, I actually have the code for making a layered plot like this, because this is not something SAS natively does. So I just put it here for your life, whenever you want to do this. Doing the life test estimates, getting information from life test, and then stacking it and plotting it together on one overlaid plot. That's kind of what this is. And I just want to wrap up just by looking at what happens when the assumptions don't line up. When you get a Cox model and a Poisson model that don't say the same story. And so this is a modification to the same data set, but I'm adding some placebo folks that basically I think there's something cut off here. Let's see. Oh, no, these people all instantly fail. This is right. I added a bunch more observations that are placebo people that fail very quickly. And what you get with the same typo is a different rate in the placebo group. So I modified the data set to break the violation. I just want to show you what happens. Here we get, instead of the rate being 11, It used to be 0.11 something, now it's 0.0882. So I modified one group, and you get a different rate ratio. It's not 4.6, it's 3.47. Again, this could be, right? You're not always privy to this individual data. You might just have group data anyway. And what you get is this, right? The Cox model is basically the same, okay? Which is kind of cool. The Cox model is robust to deviations from constant hazards. It just requires proportional hazards. So the Cox model doesn't really change, but the Poisson model does. It gets 3.47. Look at this is the log survival plots. And notice this is still linear. This is the treatment group. But this is totally not linear. It's very curved, right? It's going, whoa. This is a violation of the constant hazards assumption. This group is not linear. So at least for one of the groups, that modeling with a constant rate is not good. The rate in the placebo group is not constant. The Poisson survival is not good. This is not linear. And it's really reflected in this you have a different answer. Like this is not, if these line up, that would suggest that you're in a similar spot. And look what happens to the survival curves. So this is the same. Okay, so here are the placebo, the treatment folks. It still hits pretty well through. But now look at the placebo group, right? So it really underestimates the risk, overestimates the risk, right? The Kaplan-Meier curve, which is the actual experience of the people, shows better survival in this zone. These people are surviving at 0.6, but the model says 0.4, right? So there's this gap between reality, which is the Kaplan-Meier curve, and what Poisson says. Poisson is giving you a more pessimistic view now because we manipulated the data. So here's a situation where the plot says curved log survival, so not linear, not good. We have another clue because the Cox and the Poisson differ, and then you have this, okay, where you're showing kind of the survival. This constant survival function is missing a nuance in the data. There's a time. And we trust this. The real thing is we trust the Kaplan-Meier because this is actually the data. This is a single summary from Poisson regression of the data. So if you're faced with this situation, you say, what am I going to do? The answer is you actually would probably go with the Cox model over the Poisson model. Right? We go with the Cox model. The Cox model has H0 of t. It has the baseline hazard, and it allows the hazard function to change over time. And that gives you something more than a constant hazard over time. So here, the Cox model, because it has a baseline hazard, would be much more likely to track like this Kaplan-Meier curve, and it's not going to undercut things over here. So I think it's not going to guarantee that the Cox model is appropriate either, because the Cox model still has the proportional hazards assumption, which is that the hazard ratio, the ratio of the hazard between, let's say, treatment 0 and 1, that ratio is constant. But that's less of a restrictive assumption than that the hazard itself is constant. So I think this is going to be gone over in lab, but I just want to seed your brain with this. So what I mean by that is, if you have, this is H0 of t, and this is t, the constant hazards assumption means if you have, here's one group, here's treatment 0, treatment 1, this is the placebo, they have high hazards, they're not doing so well. And then you have treatment 0. This is the constant hazards assumption, that over time, hazard's the same. Okay? It also happens to be that at any given time, the proportional hazards assumption is upheld, right? The ratio of these two things, if this is 4 and this is 2, the hazard ratio is always 2. Right? It's backwards compatible. Constant hazards is backwards compatible to proportional hazards. But the proportional hazards assumption, is this. It's that, okay, let's pretend you have this. Okay, this would be compatible with proportional hazards, but not constant hazards, which is the Poisson piece. At any given time, the distance, or maybe you have the ratio of the distance, but see, this would have to be on the log scale, but basically the distance in some sense is preserved between the two hazard functions, but the hazard functions can vary over time. Everybody does, no matter what group you're in, you do like this. You might be low at the beginning. Let's say it's the surgery example. Everyone's doing bad at the beginning, no matter which treatment group you're in. Everyone's facing high hazard, and everyone goes down, and then up, and then down. This is the proportional hazards assumption, that the relationship between the groups is preserved, but the hazard function itself can be wacky. Okay, and that wackiness is captured in the baseline hazard. The baseline hazard function lets all the groups be wacky at the same way. Okay, it lets them all be like everyone's initial treatment experiences, everyone after surgery, everyone's at high risk, and then you get better, and then you have this period of, okay, I'm doing better, and then maybe a year later you have a heart attack again and your risk goes up, whatever it is. That, interesting shape is the baseline hazard, but the proportional hazard says it's got to be preserved. Poisson is way, way, way more restrictive by saying not only is the space between the groups' hazards constant, but the hazard is constant. So this is really strict, but sometimes works. And again, if it's this like macro level process where it's like you have summary, you have cancer survival in Georgia as your data set, this may be reasonable, and you don't have the individual nuancy experiences to model anyway. So anyway, this is going to be talked about more in lab, but I just want to be thinking about it. This stuff is, it's a bit esoteric, so we're trying to put pictures to it. And have a good day. Thank you.